Okay, my phone says it's 5 p.m. in Berlin, so I would say let's start with our today's webinar, which is about text mining on biomedical literature, and with today with topic modeling. So welcome everybody. Thanks for joining. My name is Martyna. I'm a data scientist at Knime in our life sciences team. For support, I have my colleague Jeany with me today, who is a data scientist too, and leading our life sciences team here in Berlin, or from Berlin.
Hello, welcome.
And she will support me today with the Q&A part. So let's start with some organizational stuff first. So you will have the option to ask questions, not live, but you can post your questions in the Q&A section, where you can also upvote your favorite questions using this well-known button, I would say. The session will be recorded and will be available on YouTube. Slides and example workflow that I will show today will be shared via email too, so you will get probably by tomorrow all those links you need for looking again into what we discussed today. And here you can see a screenshot where you can find the Q&A section. So you probably see only the Q&A and the chat in your setup. So feel free to ask questions. Jeany will help already during the presentations to go through the questions and try to reply to some, and some we will also answer at the end, or try to answer at the end. Okay, let's start with an overview of our agenda for today's session. So we will today, or I will today, give you an introduction to the Miletus platform and introduce you to the text mining extension. Then we will talk a bit more about topic modeling and the LDA algorithm. And I will show you an example workflow that shows how data can be automatically extracted from PubMed. So we will use biomedical literature, and we will do some topic modeling on this and create some interactive views at the end. And finally, we will have a Q&A session where we will try to answer as many questions as possible. Okay, so what is Knime? Miletus platform is an open source tool for data analysis that provides a graphical user interface. So with certain functionality, where you have nodes with certain functionality that can be used to create workflows. And those workflows can be used to perform typical data analysis tasks like reading different data types or from different data sources, data blending, manipulation, to machine learning, visualization, and finally reporting. And additionally to the platform, there are also different integrations and extensions available that we provide, but there are also community extensions and partner extensions available. When it comes to collaboration with your colleagues, to automation, workflow scheduling, for example, or workflow management, or even deployment, when you would like to share a web application, for example, with your colleagues, then, for example, the Knime server comes into play. Today, we want to focus on one particular extension and on the Knime Analytics platform. And here we will talk a bit more about the text processing extension. Especially for this extension, we provide also a book that gives a good introduction to text mining using Knime. And there will be also a book code shared with all of you at the end of my presentation. That gives you the opportunity to download the book for free as a little thank you for your participation. So be patient till the end of the presentation to get the code. Okay, so let's start with text mining. Text mining is a process of transforming unstructured data into meaningful information. So the whole process can contain different steps, but as every analysis needs to start with reading data and converting the data into a proper format that can be then used for further analysis. And the next step, enrichment, is a very popular task where we can add text to our terms of the text, like grammar rules, like parts of speech, for example. We can add sentiment tags or specific biology or chemistry tags, or even dictionary tags that are provided by yourself. We could do lemmatizing or stemming. And based on, so this is, okay, sorry. Enrichment is only about tagging. I'm already too far. And cleanup and preprocessing. With cleanup and preprocessing, you can then remove unnecessary noise from your text, like for example, numbers, filter stop words, do lemmatizing and stemming. So lemmatizing and stemming is a part of the preprocessing and cleanup task in text mining. Then we can also create back of words, which is nothing else than a list of terms that are available in a certain document, extract keywords. Then we have encoding and embedding as a typical task where we transform text and terms into numbers that allows us to do machine learning and further analysis, like classification, clustering, deep learning, for example, for sentiment analysis, something that we saw a few days ago in another webinar as well. Okay, for the text processing extension, so Knime provides, especially for the text mining task, a text processing extension, which provides really a huge list of nodes. There are nodes available for the for data reading, so you can read different file formats. Here, the ticker parser is very powerful and provides many different options to read PDF files, PowerPoint presentations, and really different types of data. Then you can use different nodes to transform the data into a proper document format that is necessary to use all those other nodes in Knime for text processing. Then we have enrichment that allows you to tag your data according to a certain topic, like for example here, interesting in a life science related session as the Abner tagger that allows you to tag biology data like cell lines or genes, or the Oscar tagger that allows you to tag chemistry data. And today we will also use the dictionary tagger that tags data according to our customized list. Then we have different nodes that can transform your data into numbers. So there are different possibilities to calculate frequencies, for example, like the term frequency or the inverse document frequency. There's a huge list of nodes for preprocessing, like the case converter, different types of a stemmer or a lemmatizer, punctuation eraser, and so on. And then additionally, we have some nodes that allow you extracting keywords. Node that we will use today is the topic extractor that uses the parallel LDA. I will come to that topic later. And then we have some additional nodes where you can create a tag cloud or view the document in a nicer way than only in a table. Okay, so today we will focus on topic modeling. Topic modeling is a very popular method in text mining with the goal to extract a hidden thematic structure of a document and can identify topics that best describe a set of documents. Of course, if a human being reads a text of documents, he will be able to define a topic as well. But with a large amount of documents, we don't have the human power anymore to do that manually. So this is the time where topic modeling comes into play. So in topic modeling, we basically start with a large collection of documents as an input, and then in the output we will get a list of documents that have an assigned topic, and every topic has an assigned list of sequences that define somehow the topic of the document. And of course, every document consists of a mixture of different topics, and at the end we will have the most relevant topic for this document in the results. Okay, so what is a topic model at the end? As we are using documents that are not labeled, a topic model is an unsupervised machine learning model and is based on a probabilistic framework. So all the algorithms that are available use probabilities to calculate topics or to predict or to structure the documents into topics. And there are different algorithms available, like, for example, the latent semantic analysis, or I think the most popular in this area is the LDA algorithm, which is the latent dirichlet allocation, published by David Bly in 2003. So I added some references here on the bottom. And today we will mostly focus on the LDA, as this is the algorithm that we use in Knime to implement topic modeling. Okay, what you can see here is an example from one of the publications from David Bly. And what they did is they took 250,000 articles from Nature and applied topic modeling on that data, showing always the top 10 words of a certain topic. Of course, Nature provides much more topics than only 5, but here's only a selection. And based on the terms, you would be able to give to every topic a name, right? So for the first one, we see this is about DNA and sequences, RNA, cDNA. So we could say in general, this is about genetics. Here we could say something about channels, right? There's a receptor, there's a membrane. So this is related more to channel research or receptor research. Then we have something about glucose, then something totally different than the others. So this is about stars and solar and galaxy. And the last one shows a topic about viruses and infections and vaccines. And of course, every topic or every document is a mixture of a topic, as I said. So it could be that a topic is, or a document has 80% of topic 1 and like 20% of the virus topic in it. But then the main topic will be, let's say, the most, the topic with the highest weight. Okay. So this method is in general useful to summarize and organize your documents. So based on this, you could say what a particular document is discussing without reading this document. You could also use the topic modeling results to say how similar two documents are, or if you are interested in one particular topic, you can then decide which document you want to read first. So a kind of a recommendation engine. There are in general different areas of application for topic modeling. A typical example might be the analysis of forum posts, product reviews, news articles, or books, for example. But Bly says in his publications that there are also applications in bioinformatics. So I became a bit curious and did some more research on that. And also in the life sciences and biomedical research, analyzing reports, different documents, scientific news, or in general, textual data is a very popular use case. But additionally to that, topic modeling was applied to genomic data, to DNA sequences. So they break down DNA sequences into subreads, and they run topic modeling on that to explore the functional and taxonomic structure of a DNA sequence. So this is about genomics, and also there's also a publication explaining how topic modeling can be used to group or structure chemical data, so with a chemical structure as an input. And especially for this example, there is a workflow available already on our hub. So if you are interested to see how topic modeling can be used for chemistry data, you can just download the workflow from there and just run it and see how it's working. Okay, this brings me to our today's example. After mentioning some examples and applications that are relevant to life sciences, let me show you today's example that covers where we keep it a bit more traditional, and we will analyze scientific literature, so no sequences, no chemistry data. And this literature we are gathering from PubMed, so we will start with a list of diseases that we previously randomly selected from OMIM. which is a catalog of human genes and genetic disorders. And from this list, we select some diseases. Based on the selection, we will create a PubMed query that then automatically will gather the data. We will create a corpus and do some pre-processing in order to be able to run the topic extractor model. Finally, we will create some interactive views and visualizations and look a bit into the results. So we will investigate the terms and the topics and see how good our model is. Before we move to the workflow of this use case, let's focus on the topic modeling algorithm that was used for the implementation of the node in Knime, which is the latent directed allocation. So in general, the LDA is able to find automatically topics with the most relevant words discussed in a collection of documents. Those documents are, as we said, unlabeled, so therefore it can be considered as a unsupervised method. And the LDA also represents documents as random mixtures of topics, of latent or, let's say, hidden topics, where each topic is characterized by a distribution over words. So we have overall 2 distributions. Each document is modeled as a distribution of topics, and each topic is modeled as a distribution of words. There are also some additional assumptions that can be made about the LDA. So, for example, the syntax and the order of the words is not important, as this is considered to be a back of words model, and the document order is also not important. So you could sort the words and the documents. This should not have any impact on the results. The same word can also belong to different topics. This is important to know. And overall, the algorithm is not able to select the number of topics, which means we need to provide this information in advance, right? So we, in the ideal case, we would need to know how many topics are included in our corpus. There are methods how you can optimize this number. I will come to that later. But for now, you just need to know we need to provide a number of topics that need to be selected in advance. Okay, there are 2 different parameters, hyperparameters for the distributions I was mentioning before. So first, for the distributions, for the distribution of topics, we have alpha. That controls the per document distribution. And then we have, for the distribution of words per topic, we have beta that controls the per topic word distribution. Why do we need this mathematical information about the hyperparameters? This is the reason. So this is the node that was used, this was the node that was implemented for topic modeling in Knime. And in the configuration of the node, we need to set, of course, some parameters. Additionally to the selection of the document, of the corpus that we want to use for the topic modeling, we need to add the information about how many topics we want to model and how many words per topic we want to see then in the results. And we need to select an alpha and a beta, right? So if you increase alpha, this will make documents to appear more similar to each other. And if you increase beta, this will make topics to appear more similar to each other. Okay, additionally, we need to select the number of iterations. So we will stop after, in this case, 1000 iterations. And in general, there are different versions of the LDA available that focus very often on the performance of the algorithm, like the algorithm used for this implementation. So this is the parallel LDA, where you can select the number of parallel threads you want to run, which makes the algorithm then a bit faster. Okay, and this brings me already to my demo, to my example workflow that I would like to show you today. Let me switch to Knime. And this is it. So you saw at the beginning, we will select some diseases. We will create a corpus from PubMed, right? So here in the very first step, we will select some diseases from a list that we already uploaded. Then we will create a corpus, download documents from PubMed. We will do some pre-processing on that, a cleanup of our data set, and then we will be ready to do topic modeling, and finally create some visualizations or interactive views here. For this, we will need to reduce our dimensionality, add some colors, what happens here. So right after we selected some diseases, we will then end in the interactive view. Let me quickly show you how this looks like, so you know what will be the final result and why we are doing some tasks. So this is how our interactive view would look like. So we will have a scatter plot. So you see now why we need to reduce the dimensionality to be able to show all documents with the assigned topic in a two-dimensional space. And you see the colors that are depending a bit on the PubMed query we made at the beginning. So I will come to that, all those results later. So you see here we will have some more information provided about the topics, terms, and the documents all in one view. And finally, we will create a tag cloud with some additional information about the documents. Okay, let's start at the beginning. I will go now through all those steps in more details in the configuration. But before I do this, I would like just to make sure, just to make clear what are the differences between those things you see here. So what you see here are nodes, are typical nodes that you can use, that you can search for in the node repository, right? They are slightly different to what you can see here. So this is a meta node, and this is a component. So those meta nodes and components you cannot find in the node repository, right? So how you can create a meta node and a component, let me quickly show you. You just need to select some nodes, and you can then do a right click, and you can create a meta node and a component. You might now ask yourself, okay, why do I need a component? Why do I need a meta node? So this could be a very long story and training and explanation now, but let's try to keep it simple. So whenever you want to structure your workflow, use a meta node. This will hide a bit of your mess. If you have any messy workflows, I have, my workflows are always quite big. And then you can use a meta node. You can just do a double click and you will see what's in there. So new tab opens, you can see what's in there. If you create a component, so you can also select here the nodes and you can create a component. The difference is a component can be used to create interactive views, like we saw in the interactive view at the end, or even here. We have an interactive view that allows us to select some diseases from our provided data set. So you see we selected 5 diseases. This is a twin list where you can just move your data going back, right? So we selected those diseases, and if you look then in the output, you will see those are the 5 diseases we selected. You can also see what's in the component. So you need to press Control and double click, and then you will also enter the component where you see that the content is pretty simple. So we are reading in the very first step a file that contains all our diseases, and then we use a widget node that creates a visualization in the interactive view. Okay, once this has been selected, so you see action needed, we need to select something here. Once this has been selected, we will create a document corpus from PubMed. So we will automatically extract data that contains those information about those diseases. So in this case, we will always select around 300 documents, if there are 300 documents about a certain topic. And how this is possible, so for this, we will run 5 loops. So every loop, one loop for one iteration of a loop for every query. And then inside of this loop, we create a PubMed query using the document grabber that is able to give you at the output all those gathered documents from PubMed about a certain topic. As we are now in one current iteration, you see here at the end there are only 300, and when we do it 5 times, so we will have 1,500 documents in our corpus at the end. And very important, you need to create a temporary directory using this node in order to be able to use the document grabber here. What you see here in the output might be in the first moment a bit confusing because you see only the title of this documents, but there is much more. So what you see here in the on the top, on the column description, there is the different type of format, which is the document type, and this allows you now to use text processing, different text processing nodes. In order to see what's inside of such a document, you can use the document data extractor that then allows you to select some additional information. There is title, there's the abstract. Let me show you how this looks like in the output table. So you see there is the title in the string format, right? There is the abstract, the text. Then we have the information about the author. We have the publication date, that might be interesting too. And at the end, we have some meta information, which is, for example, the PubMed ID. Okay, once this is done, we should have 1,500 documents at the end. And from this, we will select only 2 columns, which is the document column and the PubMed query. That looks like this. The PubMed query will not be used, of course, for the topic modeling algorithm, because this would mean we would label our data already before. This will be used for the visualization to see somehow how the topic modeling was working on our pre-selected data sets. Okay, once this is done, we have our 2 columns here, and we can start with the pre-processing. As I said, pre-processing is a very important step in text mining. So if you don't clean up your data set in a proper way, you will have a lot of garbage then also in your topics and your terms. I will show you also an example what happens if you don't do proper pre-processing here. So what I did is I used the punctuation eraser to remove the punctuation, the case converter to move to lowercase. Then we remove all stop words because we don't want to see them in the topics and in the terms. And I remove all characters that are smaller than 2 characters, right? So everything that has only 1 character will be removed. And then once this is done, we will have an additional column that is called preprocessed document. And then we can start with the topic modeling. And this is the node I showed you already before, so you know already how the configuration looks like. We need to select a preprocessed document. We need to provide a certain amount of topics. And in this case, I selected 8. Of course, you could select 5 because we selected 5 diseases. So you would expect then that topic modeling should have all those 5 and should create a very clear model according to those 5 topics. But I was just curious if there is something else in the documents that will create a totally different separate topic that I didn't expect before. So I selected 8. And then we want to see 20 relevant terms for this topic. Then we have alpha and beta that I explained already before. And we have the number of iterations and number of threads that I just left as a default value. Okay, so you see this node contains 3 output ports. The first one is the document table with topics. Then we have topic terms, and then we have some iteration statistics that we will ignore for today. So in the first one, we have the document table with topics. So we have our document, and we have the information about the topics and the assigned topic. For example, here, the first document is assigned to topic 1, and you see topic 1 is here and had the highest weight compared to the others. Okay, and then we have in the second output port, we have the topic ID, the term, and the weight. So we see what are the terms that were selected for a certain topic. So you see here, topic 0 is about diabetes. So, and surprisingly, we had diabetes as one of the diseases I selected at the beginning. And you see the weight. So you see basically on this, based on this, you see the most relevant words first. So we will use this information now to create an interactive view. In order to do this, especially in order to do the 2D scatter plot, we need to reduce some dimensionality. Here for this, I use Jeany, which is a popular method to do dimensionality reduction, especially for creating visualizations. And you can see here, you can select how many dimensions you want to have at the end. You have some additional parameters that you need to select. And then at the end, you will get 2 new columns, which are here at the end. Then we will add some colors, and we will color our data according to the PubMed query. So you see every disease gets a different color. And already in the output port, you will see the assigned colors to every document. Then we will join the data that we have here with the information about the terms per topic. And then with this information, we will create an interactive view, the interactive visualization. You saw before that this interactive visualization contains 3 tables and a scatter plot. So for this, we need to prepare our data first. So we will use group by nodes that group over certain columns in order to reduce the data and condense the data a bit for one particular column. And here, for example, you see we group according to the assigned topic. So we get a unique list of topics. Here, for example, we have some more columns selected. And we get at the end a more condensed version of this information. So we will remove duplicates in this case in order to create the scatter plot, for example. And then we have the terms per topic that would bring us again to this list with this information. Okay, very important in interactive views is the order of the order or the layout what you want to use for the visualization, right? So if you just add the nodes, they will be randomly shown in the view. And what you can do is when you are in the component, you can use the visual layout editor that then allows you to move and to change the order and the size of the visualization and of the table. So you can add additional parts here and just move around all your tables and plots. Also very important, this is an interactive view, which means we want to be able to select something in one table, for example, or in a scatter plot, and then also be able to see an updated version with only the selected data in another table. So for this, it's very important to select the enable highlighting whenever it's possible in the component. So this, with this, you can make sure that the visualizations and the tables are able to talk to each other. So the row ID will not get lost in this case. Okay, let's look now into the interactive view. Okay, and what we see here now in on the top in a scatter plot are all our documents that we colored according to the PubMed query. So you see, or you maybe might think there are already some groups with similar colors, right? So, and you're right. So we have a group for diabetes. We have a group for pheochromocytoma. For the I select also Prader-Willi syndrome. There's rheumatoid arthritis, and we have alcohol dependence as another one. And we have some others here in the middle. So let's see if when I select now one topic, if this is really true. Oh yeah, I mean, you see now all those documents are grouped together. They are most likely light blue, so this is diabetes. And if you now go to the bottom, you see that you see the terms of one particular topic, and you see that this is about diabetes. So this could be the title for our topic. And you see terms like insulin, Miletus, glucose. So all those topics, all those terms are relevant to this topic. Okay. Let's show topic 4. I will go through all the topics, but I have my order. I want to show you the topics today. So let's look at topic 4, which is most likely the Prader-Willi syndrome. So the Prader-Willi syndrome is in general a genetic disorder. So you have words like genetics and so somewhere disorder. And newborns, for example, it includes symptoms like weak muscles or poor feeding or slow development. But beginning in the childhood, the person becomes constantly hungry, which often leads to obesity and type 2 diabetes. And if you look into the terms, you will find words like children, obesity, for example, which also informs you a bit already about the disease, even if you don't know the disease from the very beginning. Let's look at topic 5. This is the alcohol dependence, and if you now look into the terms of this topics, we see there is alcohol dependence at the top. Words like drinking, consumption, substance, drug. All those terms are related to this disease. Topic 6. Here we have the documents about the pheochromocytoma, which is in general a rare tumor of the adrenal gland tissue. So you see words like adrenal tumor, and then it results very often in hypertension because of the release of too much epinephrine and norepinephrine, so hormones that control the heart rate, for example. So hypertension also makes a lot of sense here. And then we have topic number 7, which is about obviously about arthritis or rheumatoid arthritis. We have the abbreviation here with the highest weight. And if you go down, you see terms like inflammatory, autoimmune, that all describe somehow the disease. And you see also here at the almost very end, there is MTX, which is an abbreviation of the drug that is frequently used for the treatment of rheumatoid arthritis, for example. So all those terms make sense. So you remember I selected at the beginning and the node configuration 8 topics, not only 5. So those were the, I would say, most obvious 5 topics that I would expect from this model. But I selected 8 in order to see what else can be maybe extracted or extracted from these documents. So I skipped topic 1, 2, and 3, and let's look into those topics now. So you see topic 1 is not a small topic. So there are many documents included, and they are quite colorful. So we have documents from all those different queries we selected at the beginning. And let's see what's in there. And you see the very first words already say something about the topic, which is cell expression. So those documents are most likely about cell expression, about signaling. There's pathway analysis. So it seems that in those publications, that cell expression topic was more present than the PubMed query or the disease we selected at the beginning. Let's look at topic 2. So here, topic 2 is also mixture of different colors or different diseases, and we see here this topic is most likely about patients and patient studies. At the end, you have the word cohort, which is quite often used in clinical studies reports, right? But we have also something like 95 or CI. So if we would now do some in the pre-processing remove numbering, so we would not see the 95 anymore. But nevertheless, the 95 makes me curious, and I want to see what 95 means. So for this, we could now leave the topic selected, close and apply, and then create a tag cloud, and get some additional information about the documents that contain the number 95. So here you see the 95. Let's select this one, and in this view you see there's additional information in a table below, and you see already here there is the number 95% confidence interval. So this is here we also see confidence interval written without using only the abbreviation, and you see the 95 is most likely about confidence intervals. So with this you can explain what some words might mean. Of course, if you don't want to see it, you need to do a better pre-processing. With this, we would need to do to remove just the numbers. In order to remove the CI, we would just need to increase the number of characters in our pre-processing here. But there was another topic, the last one, that looked a bit strange at the beginning. Which is topic 3. And you see there are not that many documents assigned to topic 3, but if you look at the terms, it's like a garbage collection. I don't know, it's like trash, right? So you have it seems there is okay, if we ignore lung and pulmonary, you see this is a mixture of different languages. So I see German, there is probably Spanish, maybe French, I don't know. So let's see why those terms were selected. So what are the documents about? Because if you look into the titles, they seem to be written in English, right? So let's select this one. Create a tag cloud. And then you will see here all those strange words that we didn't expect. Let's select the one that I know that is that is coming from the German language. And if you now look into the abstract, you will see that part of the abstract is written in English and the other part is written in German. So it seems that the topic really makes sense. In this case, you can, of course, do some additional pre-processing. Know that you have different languages there, so you can also remove documents that are written in a different language than English, for example. Okay, so this is about the analysis of our topics. And here, finally, we create, as you were able to see, the tag cloud. And let me show you quickly what happens in this component, so you know how to create a tag cloud in this interactive view. So you saw we selected in the previous component a topic, and this is the data that will be now loaded here, right? So we have all this information about the topic, all the terms. And then we need to first tag our documents using those terms. So we will use the dictionary tagger to tag the documents according to the terms that we have in topic 3. Then we need to filter those terms because they will not be visible, right? So for us, they are hidden here in the document column. So we need to filter those terms. We will create a bag of words that adds a new column, which is the list of terms. So now we have all the terms that occur from this list in our document. Then we need to add some numbers in order to define somehow the size of a word in the tag cloud. So here the inverse document frequency was used, but you could also use the term frequency as well. So you see we have some frequencies now at the end. And the tag cloud expects two things. One is the frequency and the other one is the term, and the term needs to have the format string. So we need to, let me quickly show you how it looked before. So you see this is a different format. This is the term format. We have here the document format. And in general, in text processing, we have these two very important formats that you need to use in order to use the nodes. And then we can just transform this term format into a string, and now it looks much better, and now it can be used also in the tag cloud. Additionally, we extract the information from the document that contain the abstract, that we were able to see the title and the publication date. Right, and then we see also this information here in the table. Okay, so this is how the tag cloud was created, and this is in general the workflow that I created for this for the session. So you learn how to extract data automatically from PubMed, how to do some pre-processing, how to run a topic model, and then how to create an interactive view and a tag cloud using Knime. Let me quickly go back to my slides to show you the link where you can download the workflow. Don't worry, we will share all those links after the webinar, probably by tomorrow. So you will be able to find the workflow without any problems using these links. And there are also other examples that I would quickly want to show you too. If you are interested to learn more about text processing using Knime. So I mentioned before, there is a method that can be used to optimize the number of topics. So there's a blog post available about that with a nice workflow that you can download as well about optimizing the number of topics with the elbow method. And there are also other life sciences related examples that show how, for example, how you can detect disease names that were not part of a training data set. So there is a machine learning model behind that is able then to detect new disease names and creates a co-occurrence network that shows diseases, the already known diseases and new diseases as well. So there's information where you can find some more about this example workflow. So there's the blog post and there's also the workflow. And this is something you saw already a few days before, presented by Julian, who showed how you can predict the purpose of a drug. So there's also a webinar recording if you want to